Hi everyone, so this is Team 16 again for the OpenLitho for most likely the last time for this semester. So as a quick reminder, our initial goal is to bridge between the industry standards, which are extremely high, extremely impressive. Here you have ASML's extremely ultraviolet lithography machine, which reaches 13 nanometers of precision, but also has a cost of many hundreds of millions of dollars. So it is very precise, but also very inaccessible to most makers and most small researchers. And this is where we come in, actually. Through our project, we've aimed at producing a system that is a very small fraction of the cost. Of course, for students that want to have a few hundred thousand dollars. We have more money with donations, but overall our goal is to make it more available for DIY makers and researchers, and also having, like, of course, a less performative system, but still sustainable for MEMS projects, macro electromechanical system projects, which is a huge field in DIY making and also in very small scale research. So here you can see our system actually performing in live. So we've been able to pattern through the red laser, which you can see on the image. It is reflected off the mirrors. And then we're going through part of the optical train to clean up the beam profile through the iris that you can see over there. You see how the beam diameter changes as we focus. After that, we go into the galvanometer mirrors, which produce the rastering pattern. You can see there's a square. And then this big box is a VCM, a Volschool motor, to adjust the focus. The light is later routed up and then further routed down in order to be able to have the space to put the objective and the wafer with the vacuum check all together on the breadboard. So you can see here our actual screen, which monitors the pattern, and this is the pattern that we're imaging, which was a square, as I mentioned, with decent clarity and decent resolution. So how does it actually work? So as I mentioned, we have a red laser, which is the 640 nanometer laser for alignment, but we also have a UV laser that is used for the curing of the photoresist. Once the light is on, we'll be using a mirror to first reflect the red lights, which will then pass through the dichroic mirror. The dichroic mirror then selectively reflects the UV light that will be turned on for the curing of the photoresist. After that, we have a collimating system, so two lenses that are positioned such that the light will then be at theoretically constant diameter over very long distances. And so first, this is the first advantage, and second advantage is that we can use that collimator to clean up the beam profile using the iris that you can see in the middle there. And then within the collimator, you have a beam splitter that splits half of the light into the power meter. So as the name says, it splits the light into the power meter to modulate the light's intensity to adjust it to the to the photoresist. And the other half of the light goes into the galvanometer mirror, which are two mirrors that move in coordination to produce the rastering pattern. And after that, once we have the rastering pattern, we'll be able to use our autofocusing infrastructure. So we have a first lens and a second lens to form another collimator. So like previously, but the main addition is that we have a Volschool motor to move very precisely a very weak lens of 1000 millimeters to have high control over the focusing onto the substrates. And then finally, once this is done, we're able to later image onto the substrate directly, so light goes up and down as we saw in the video. And then since the substrate reflects some of the light, we're able to monitor that reflected light onto the camera. And then look at it on the screen, which will then allow us to kind of adjust for the focusing through the Volschool motor that we mentioned previously. So this required many things for the realization. It required, of course, quite a good amount of machining. Actually, quite a very good amount of machining. Many chips were made for that project. We also had a good number of simulations. Here you have simulations for the laser mounts to confirm the design of these very important elements, but we also had a huge amount of work that was done on the optical side to better understand the objects, since none of us had such an intricate understanding of objects before, but we were able to learn and develop as the year went through. And I would say that generally through working on our system, the different aspects of our system, we're able to improve ourselves and improve the system along with us, and we believe that we can keep going, keep working, keep making OpenLitho better, more available, more modular. And hopefully this is something that our DIY community can later pick up and improve as a global project for everyone to contribute and benefit from. Thank you.